Machine learning gets tossed around like everybody already knows what it means. Most people know the word, but almost no one knows the 5 types, or where each one breaks. Let's fix that. Supervised learning. Supervised learning is the most common type. The idea is simple. You have inputs and you have labels. You show the model enough examples and it learns the mapping between them. You show a model a million examples, like cat, not cat, 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 and definitely not a cat. And it learns the pattern. But how does it actually learn? It guesses, and it checks how wrong the guess was, and then adjusts it, and then guess it again. Like a student doing a practice exam, except it does 10 million practice exams overnight and never complains. That number measuring how wrong it was, that's called a loss function. The model's entire job is making that number smaller. So why does it ever go wrong? Because you only ever learn from your data, specifically your data from a specific point in time. And here's the problem. The model doesn't learn the truth. It learns a pattern in your training data. If your data was collected in 2022, you will know 2022. Put in production in 2026 and the world has moved, customer behavior has changed, and the market has shifted. And the model doesn't know, and it keeps predicting confidently into reality that no longer exists. And that's called distribution shift. The most common reason the production models quietly degrade and the model's confidence score won't tell you that it's happening. But when your data is clean and the world is stable, supervised learning is the most reliable tool in the entire field. It's well understood, well tested, and it works. Which is why it's still the default for almost every production ML system in existence. Semi-supervised learning. Labeling data is expensive. A radiologist reviewing 10,000 scans and a lawyer tagging 10,000 documents. You might end up with a few hundred label examples and a million that you never touched. So what do we do with all that unlabeled data? Throw it away? Semi-supervised learning says no. The labeled data teaches the model what things are. The unlabeled data teaches what the word looks like, the shape of the distribution, where the natural boundaries are. The model uses the instructions as an additional signal. Think of these like learning a language. Someone corrects you.
No.
Corrects.
Yeah.
Corrects. Someone corrects you in 100 sentences. But you also live in a country, observing the accent, slang, sentence rhythm, the patterns how people naturally speak. The corrections are the labels. Everything you absorb just by being around their language is the unlabeled data. This works because of a core assumption. Data points close together in an input space probably share the same label. The unlabeled data helps the model understand that space better. But that assumption is the problem. Take the word polvo. In Portuguese, it means octopus. Spanish and Portuguese look similar, sound similar, and share thousands of words. If you speak Portuguese, it feels natural to assume that the same words carries across in Spanish. But in Spanish, polvo means dust. In Spanish slang, it means something else entirely. I'll let you find that one out yourself. The unlabeled data points you to a completely wrong direction, not because the pattern wasn't real, but because the assumption that similar looking things share the same meaning just doesn't hold here. It can actually push the model into the wrong direction by learning the patterns that are not real. And the problem only becomes visible later, when something downstream fails. But when the assumption holds, semi-supervised learning lets you build models that would otherwise be impossible. You get the performance of full supervised models without the cost of labeling everything. It feels like medical imaging and speech recognition is not a nice to have, it's the only practical path forward. Unsupervised learning. No labels at all. You hand the model the raw data and ask to find the structure on its own. No right answers, no wrong answer, just what is inside here. Imagine you give a computer a list of restaurants in London. No cuisine, no categories, just names, location, prices, visit times, and average order value. And you ask, find the groups. That's unsupervised learning. It doesn't know what Italian means, it doesn't know what sushi is, it just sees numbers and patterns and find them. Maybe it groups a pizza place in Soho with a sushi place in Chinatown and a tapas bar in Angel. Not because they're all Asian or all European, because they're all mid-range, all busy on a Friday night. The computer found a real pattern. It just wasn't the pattern that you expected. But here's the thing, it might also group every restaurant that starts the letter I together. Itsu, Iberica, Iboreto, Japanese, Spanish, and Italian. Nothing in common except the first letter of their names. The algorithm found a pattern. It's a real pattern, but it's completely useless. And that's the evaluation problem. The computer grouped those restaurants, but it has no idea what the groups means. It can't tell you why they are together, it just knows they are similar. You are the one who had to look at the clusters and find out if it means anything at all. But that's also exactly what makes it powerful. Because sometimes you don't know what you're looking for. No predefined category, no assumptions baked in, just patterns that the data already contains. And that's how researchers discover cancer subtypes that no one knew before. How companies find segments that were never thought of to define. Sometimes the most valuable insight is the one that you weren't looking for. Anomaly detection. Anomaly detection has one job: learn what normal looks like and flag everything that doesn't. Fraud detection and network intrusion, manufacturing defects, equipment failures before it happens. It's like a bouncer who memorized every regular. And the moment an unfamiliar face walks in, they get stopped. Simple enough. So, when does it break? The obvious problem, defining normal, is harder than it sounds. You train on historical data, the model builds a picture of a normal from that snapshot, and then something new appears in production. A new product, a season spike, a system change. The model has never seen it, and it looks like an anomaly, but it isn't. Your model can't tell the difference between a genuine threat and something that is simply new. Both look identical from the model perspective, and then there is a class imbalance. Real anomaly are rare by definition. One fraud transaction and 10,000 legit ones. A model that predicts normal every single time is 99.99% accurate and completely useless. You have to actively correct for it, or your math works against you. Get it wrong in either direction, you either will miss real threats or generate so many false positives that your team stops trusting the alarms. Both outcomes are expensive. But when it works silently and constantly at a scale that no human team can match. Every transaction your bank approves in milliseconds, every packet that your network lets through. Anomaly detection is the reason that entire categories of frauds, intrusion, and equipment failures get caught before anyone ever noticed that happens. Reinforcement learning. This one is a completely different. No data sets, no labels, nothing. Just an agent, an environment, and a reward signal. The agent tries something, gets rewarded if it works, it gets penalized if it didn't. Does this millions of times, gradually figuring out what works. It's the same way a toddler learns to walk. No one shows them a diagram, no one explains the physics. They fall. They adjust and they fall again, and eventually they'll figure it out purely from feedback. The difference is the toddler has common sense. The Asian doesn't. This is how AlphaGo became the best Go player in history. How robots learn to walk. How recommendation systems learn to keep you watching. So give it a life if you made it this far. Let the algorithm know that you like your videos. All of it learned this way, from trying, failing, adjusting, and not from labeled examples. So what's the problem? The reward function is the entire specification from what you want. And it has to be exactly right. The agent optimizes it completely without understanding of your intent. There is no common sense, there is no implied goal, there is only the numbers and just make the number bigger. OpenAI trained a boat racing agent to go fast. The agent discovered it could score more points by spinning in circles, collecting bonuses, than finishing the race. The reward was specified correctly. The agent solved it correctly, and that's called reward hacking, and it's not a rare edge case. And beyond that, reinforcement learning needs massive amounts of experiential work. In simulation, that is expensive, but tractable. In the real world, those millions of failures has consequences. So you simulate, but the simulation is never the perfect replica of reality. Slightly different physics, different latency, and different sense of noise. The policy trained in simulation hits the real environment and it doesn't transfer. But when all that is solved, reinforced learning does things that no other approach can. It can be the best Go player in the world is teaching robots to perform surgery. It learns strategies that no one programmed, no one anticipated, and no one fully understands. And that's either the most exciting thing in machine learning or the most terrifying one. Probably both. So that's the 5 types. Most people who use machine learning mean supervised learning, and that's it. That's the whole thing that they are picturing. Which means every time someone says, we are using AI for that, they probably imagine 1, 2 out of 5, each with a completely different assumption, different failure modes, and different costs. The tool isn't the hard part. Knowing which tool and where it breaks, that's the hard part. And that's what separates someone who uses machine learning from someone that understands it. If that was useful, you know what to do. Like and subscribe.